Thank you. First check. Can you all hear me? People in the back. Excellent. All right. So I'm really excited to be here. Thanks for inviting me to speak. I heard that my audience today has various backgrounds. Things that I'm going to talk about here today is going to be mainly image-based. So I expect many questions. Please feel free to interrupt anytime. If something is unclear, raise your hand and we can talk about it. I love the type of talk where we are interactive. So let's do that. So I'm going to talk about this new work of mine called TCAV. This is work with my awesome collaborators, Martin, Justin, Carrie, James, Fernanda, and Rory at Brain. So as Kevin briefly mentioned, my research agenda is interpretability. How do we make machine learning models more understandable by humans? Humans in particularly who don't really know machine learning. I care about interpretability because this machine learning is a very powerful tool and we want to use it responsibly. What does that mean? That means that we ensure our values like fairness is reflected and our domain expert knowledge, like doctors' expert knowledge, is appropriately also reflected. So here are one ways to categorize interpretability methods. First one, you can do something before you build any models. And this is typically called exploratory data analysis, visualization, and so on. So facets, or my work, MMD Critic, which selects prototypes from complex data distribution to give you a sense of what your data distribution look like, falls into this method, this category. And if you have power to build a brand new model, that you can replace the existing one, or you're starting from scratch, then you can build a model that has inherently interpretability embedded in it. So BCM or glass box falls into this category. But often case, you don't have this power. Maybe you're given a complex model that years of engineers had debugged and empirically tested. So you are given a model, you can't change the architecture, you can't even retrain it. Then what do? So this work is about the last type of interpretability method. You're given a model, you can't change it. How can we still improve interpretability? So high-level goal goes like this. We are interested in using high-level concepts of your choice, you, the user, to explain whether that high-level concept was important for a prediction of this network and how much. For instance, to give you a concrete example, let's say I build a neural network that tells, given an image, whether this is a doctor or not a doctor. I'm interested in knowing whether this network cared about gender. So did it matter that this picture happened to have a woman in it and not a man? Did it influence the doctor prediction? And where this gender concept is what I'm interested in, and I gave some examples of what I meant by gender, positive and negative examples, to the network. So before we talk about this new method, let's take a look at existing method. Who is familiar with saliency map? Some folks. Great. I'll explain in next couple of slides. It's pretty simple. Saliency map is a method, an interpretability method for typically image-based network. It looks like this. You take the logic layer of a particular class, so in this case, doctor class, and you take derivative with respect to every single input pixel. And what that does is, if I change this pixel a little bit, what happens to my score for doctorness, or the doctorness? If it changes a lot, that means this pixel is important. If it doesn't change, then pixel is not important. So it looks like this. For instance, the top image is a dog, and it's impressive. Like the top image, it's a dog on a white background, it's a white dog, and it puts importance on the pixels on the where the dog is. So that makes sense. And it says, yeah, prediction was this type of dog, and these are the important pixels. Second picture, it's a cat and shoes, and it thinks it's a pair of shoes, and it doesn't look at the cat very much. So that's cool, but when I look at the second picture, I wonder why it wasn't a cat. Was it because it was a black cat? Was that less black cat in your training data set? Or was it because the cat was looking away? Let's look at some more complex examples. Here are two images where the ground truth was cash machine. So on the top, there's a right-hand cash machine. On the left, the first one was correctly predicted as cash machine. Second one was sliding door. And I want to know why one was correct and the other wasn't. Like, did it matter that there are some pixels on the human on the top picture? Did it matter that human was sitting in front of the machine? Did the human concept matter? Or the glasses concept in the bottom picture matter? Or the fact that this person was holding a piece of paper, did that matter? Yes?
Is there an assumption that pixels are
Yeah, well, yeah. So the question was there assumption in generating saliency map that pixels were independent? Yes. So we do, when we take that derivative that I wrote down, we do independent of each other pixel. So there's no communication between the pixels. Right. So this is right. So this is not my method, but there are other. This is the simplest type of saliency method. But we do have not we, but the machine learning community do have other more sophisticated methods where you consider a region instead of one particular pixel. But this is the simplest kind of question. All right. So this, when I look at these pictures, I wonder, well, did the concept human matter? Glasses matter? Which one mattered more? And is that true for entire class of cash machine, not just these two pictures? And that is all to say we need quantitative global explanations using any concepts that you chose, instead of giving you explanations based on pixels, input pixels of the picture. So that's what we do. Our work TCAV's goal is to produce quantitative explanations, how high-level concepts of your choice were important for this prediction or not important. And these concepts are provided, can be something that the model didn't know ahead of time. So for instance, Inception V3 never learned about gender. In fact, it doesn't have any prediction classes that relate to humans. It just says like objects, apron, water bottle, and dogs, bears, and tigers. But we show that we can still extract gender and race concepts from these networks who didn't know about gender or race and estimate the importance of such high-level concepts. Our running example, as I go through the details of the method, is going to be stripes concept. We're gonna see if the stripeness concept was important for zebra predictor, zebra class, or not. So that's our running example. Your first question might be, well, how do you define this concept? Seems like abstract. How do you do this? It's actually really simple. You need 3 ingredients to define a concept. And we define this concept as a vector, and we're going to call it concept activation vector, CAV. Now you need examples of concepts, in this case, pictures of stripes. And you need random images, something that is likely to be not stripes picture. Then you must have a network that you're interested in investigating, and you have access to internal tensors. So in this case, function f takes n-dimension image input, maps onto m-dimensional activation in the middle layer. So we have 3 ingredients now. What do we do with it? We simply train a linear classifier to separate the concept activations of the concepts, so f of all these concept examples, to separate it from random activations. And then the concept vector becomes the one that's orthogonal to this linear classifier decision boundary. And what that vector means is taking all the random images and pulling it towards more and more concept. Yes?
How do you decide which middle layer to use?
Great question. So I'll talk in a bit about, we do some statistical testing to learn which layer has learned this representation of concept the best. And you use that. Or you might have a multiple of them, then you can look at all of them. Good question. So that's it, yes?
Because some images of stripes seems to be more like texture kind of images, whereas the second looks more along lines of objects or parts. Is that like a good way of putting positive negative classes?
It's a good question. So you can put the concept images to be anything. So in fact, later we do human faces. We get this labeled data set in the wild to get race and gender pictures. So that's fine. We've done color. So I just literally generated RGB pixels of red being red with some noise. So it can be anything. So far what we've tried, just various different levels of abstraction, it seems to work. So to answer your question, as long as the network passes this statistical testing that I'll talk about in a bit, then you're fine. That means that the concept is at least linearly separable in one of the layers. So you can do something with it. Questions? All right, so now we have CAV. How are these useful? What can we do with these CAVs? It's also pretty simple. Here's what the core concept of TCAV, which is directional derivative. It's nothing new. It's long used in physics community and many other communities, actually. What this is, in the contrast to saliency maps, is to take the logic layer and take a derivative with respect to this CAV that we just learned and see how sensitive my logic layer, or in this case, zebra-ness was. If I take a smallest step into this vector dimension, how much does my logic layer score change? If it changes a lot, that means this concept was important. If it doesn't change, it didn't care. So let's call this directional derivative, give it a name, S. And you can do this, get this score for many, many zebra pictures that you have. Then what we simply do is to take the ratio of zebra pictures among everything you had that returned positive directional derivative. What this says is, I want to get all the zebra images where stripedness concept, existence of stripedness concept was positively contributing to zebra-ness. Now you can flip this around and do all sorts of other things. You can test the absence of the concept. How much was that important for zebra-ness by flipping this, and a lot of other metrics that might fit your bill. So for instance, differential diagnosis, when doctors want to know why did this class not a Gleason 3 and Gleason 4, in that case you can customize this metric to their needs. Yes?
These zebra images, these zebra images, do you care that they were classified correctly as zebras or not? Or
it's a good question.
Do you take all the things that you know to be zebras and don't care whether the network gets it or not?
So I think it's better to take images that you think, well, actually, it's probably better, it depends, is probably the right answer. I think it's better, if you're interested in investigating models' response, then you should collect the things that model said it was zebra, right? But if you...
What I'm thinking is that instead of looking at the directional derivative when it is large and positive, you could just look at its magnitude, because you don't know what the rest of the layers after that are going to do. And
magnitude of?
Just the magnitude of the directional derivative.
Yeah, yes, you can totally do that.
Say, okay, whatever direction it is, it recognizes that it has stripes, either it's very stripy or not, whatever, and then later on another layer might flip the information and use it in the right direction.
You can totally do that, and it's completely consistent with our results, but we just wanted the score to be between 0 to 1. Yeah.
My question actually was very close. The question was the set of images you estimate share in. Is it just analyzing of the training set?
I estimate what? Sorry?
When estimate this score, the share, the TCAV, which is just share of images where your derivative was 0.
Ratio of
you
images.
just analyze the training set, or you apply your network to new
New zebra pictures.
possible zeros.
I see. The question is do we use the new zebra pictures that I collected, or was it part of the training data set? Okay. If you have a training data set, it's better to do it on training data set, but if you don't have it, as long as this classifier says it's a zebra, then you're good.
And do you use negative set also?
Negative, non-zebra?
You can keep non-zebras, like what you are
Oh.
non-zebras, like telephone
Yeah.
or something. And I don't know, calculate the opposite thing.
Yeah, totally. So that's what I think you're getting into the thing that I briefly mentioned. If you are interested in does the absence of stripes makes it non-zebra, then that's exactly what you would do.
Yeah, it can be positive for all the rules.
Yep. You can say how different is the importance in the stripes in zebra versus everything else. Yeah, it's a great idea. Yeah. If that's your interest, you can edit the TCAV score to be that and get that measured. Yes, good question. Okay, good questions, guys. So I just talked about this already, comparing the saliency method we just talked about. Similar derivative sensitivity measure, but now we're using high-level concept instead of one pixel at a time. Yes?
Do you mind going back to the picture where you had you were showing the TCAV? So it's like slides ago. I just want to see.
These guys?
Yeah. So the LVC is the VLC.
VCL.
I guess I haven't wrapped my head around how you have a derivative of the class label. Like, how is this influencing? Like, what is the function that goes from this to the?
Oh, it's just a simple. So in the limit,
I
if
see
it,
what you mean. Okay.
Yeah.
This is a separate classifier that you train only on. This.
It's a two-step procedure. You get the vector, and then you take the derivative, and then you decide which class you're interested in. Get the
This
zebra.
derivative is a function of this new model you train.
Yes,
this
yes.
New data.
Yeah, well, those two are same. Oh, it has to be the same model, right? So this model that you learn VCL from, you get the vector. What that vector means in your network of interest, how does this concept represent? Now you have that vector, and then you take the derivative with respect to this vector. It's just a math calculation. Yep.
Just to make sure I understand, in the previous slide, the blue part of the network, C, is shared between this new network and your original classifier, whereas the green part is a part that you've added on.
Oh, I see. Okay, let's reset. Let's reset. There's only one network ever. We're gonna investigate. There's only one network. The function f just is an activation function at layer L, right? So there's only one network. We learn this vector from that network, but this layer just happens to come from layer L. And I'll talk about how you choose this layer L.
Classifier. You can just identify the hyperplane at M, which separates stripes from non-stripes, and then take the derivative with respect to
Sure, that's one way to put it. So there's only one network, and then you take the derivative of that network's logic layer with respect to that vector. Does that make sense?
Sorry, the reason that I'm confused is that you said originally that you were not going to interfere with the training of the network that detects different kinds of animals. So if I understand what you just said, I'm surprised that it sounds like you have one output layer that is able to detect both zebras and stripes. And I thought you weren't doing that.
So when I say we don't interrupt the original network, I mean we're not retraining it, but we do get access of the internal tensors of that network.
But when you put in new training examples to separate stripes from other stripes,
Oh.
are you changing the right-hand layers of the network?
Oh, I see, got it. Okay, I see the confusion. So when I'm doing this, am I updating the network?
I thought you were updating. I thought the green part was totally new and the blue part was fixed.
I see. Sorry for the confusion. The network that doesn't change for this entire time of the talk is the whole thing, green part and the blue part. Okay? And we just happens to train a classifier on a layer L where only blue part plays a role. You can do this in any layer in the network.
When you say train a classifier, do you mean the green thing?
No, I meant taking...
the VLC.
Right, so this is f of L, right? Function f of L.
Yep.
And then I have these images. I pipe this image all the way into right here. Right? And then I train a linear classifier separately, completely separate from my neural network to learn VLC.
Sure, that's fine. All right.
Right, so I didn't change any part. The network stays identical, right?
No, so there is a separate thing that's being added, but it's not the green part, it's the vertical arrow.
That's correct.
I'm sorry.
That's correct, yes.
You were going to do a K-way classifier for stripes and things. It's just
I see, it's just a binary. Yeah, and once I get the VCL, I throw away this classifier.
That's
Okay,
fine.
well,
So
yeah.
these are extra parameters. Great.
Thank you, yes.
So does it mean technically that your concept is bound to a specific, like, architectural part of network, like a layer, like 2 layers, something?
I'll talk a little bit about what it means in each layer and how we confirm our, I'll talk a little bit about that in a bit. Good questions. All right. I'm glad we sort that out confusion before we move farther and show the results. Yes? before page.
So what is PZ here?
It's the logic layer probability of a particular neuron that represents zebra.
So is that an output of the final layer of the network, or just the?
It's a final layer of the network.
But the final layer output has nothing to do with VCL, right? Because you're putting a separate linear classifier on the real layer.
So VCL lives in the dimension of the internal activation layer. If you believe activation layer and look at it as a vector space, then any vector in that activation vector space is related to the final logic layer in the sense that whatever that comes out into this activation layer is going to be forward propagated to generate the final score.
So still training a real model, a whole new model. There's no training like that.
I think maybe I understand that. I have the same confusion. So what it is
Huh.
you're training, you're saying what's the derivative with the of the zebra-ness with respect to that internal layer. So if you change that M, or that you mark, you change whatever's coming out there, that will change the prediction, right?
That's correct.
And you're saying, look at that derivative, that gradient, but then look at the change with respect to this other direction, which is the VLC.
Yeah.
Yeah, if you were to move the image the pixels of the image in a direction that would make the strikiness classifier respond more strongly.
That's right, yeah.
If you make it, the strikiness increases quickly as possible, how much would that change?
Yeah, and we're doing that in the intermediate layer instead of input layer. Fantastic. Very interesting. All right, cool. All right, moving on. Any questions on this regard? All right, great. I'm curious because this is like not the first time I've given this talk. There were more confusion. I want to figure out if I can do better in my slides. Who got this idea? It wasn't confused. Who got this idea? Okay, interesting. Okay, cool. That's there might be more than like maybe I'll update some of my slides to reflect your comments. Cool. All right. So we now have CAV vector, and now we have a TCAV score. But Kevin asked this question: how do we know? Well, how do we know which layer we want the CAV from? In other words, how do we validate this CAV that we just learned? In other words, how do we guard ourselves against some spurious CAV? We're working in very high dimensional data set in dimension in activation layer. So it's possible that you learn a vector that happens to return high TCAV score. How do we make sure that we are not on that regime? There are many ways, but here's one way to do it. In this controversial picture that we talked about, we have activation where we trained a linear classifier of the activations of the concept pictures and random images. And because it's random images, you can select any set of random images that you want. And from that, you can output you each can output TCAV score of their own. This probably is, and if you view this as a sample from a particular distribution, it might look like this. What this means is that most of the time, the TCAV score outputs pretty high up here. Does that make sense? So we have learned now many VCLs by using slightly different set of random images. We calculate TCAV scores from them. Now, if you view these as a sample from a distribution, then if distribution looks like this, that means, yeah, TCAV score was in generally pretty high. Now, you can compare this to TCAV score at random. So you can train a concept, a random concept, by selecting random pictures and train that against random pictures and find what is my random CAV. How can I be random? And if you compare that and run t-testing to see whether the mean of these two distributions are significantly different. If they're different, that means, yeah, this vector that you learn, or the chances are that it is different from random. It means something. Whereas if it's not, then you shouldn't be using this layer or the concept vector that learned from the layer. So all the results that I'm going to show you here all pass this test. So I'll first show you some sanity check experiment. This is carefully structured experiment for us to have a ground truth, and we compare TCAV score to our ground truth. So you might say, well, yeah, this is cool, but how do you make sure that TCAV actually works when you have a ground truth? How does it match? Here's a setup that we made up. We have images of 3 classes, cab, cucumber, and zebra. Then I literally went and wrote this word cab in every single images. And we made these captions sometimes pretty noisy. So if there's a cab in the picture, sometimes I wrote tiger. And I varied that set noisy level and made 4 different training sets. Now I'm going to train 4 different models. And each model, by doing this, each model has a choice between looking at the image or the caption for classification. We know which concept it paid attention to by doing this test. If we give it a test image without a caption, and if it does well, like this case with no captions, that means, yeah, it learned to look at the image. If it does terribly, that means that, oh, it looked at the caption. Does that make sense? All right. So that's going to serve as our ground truth, and we're going to see, and this can be viewed as the importance of the image concept, and we can compare this to TCAV score for image concept. So here's the result. We tested 3 classes, but I'm showing you 2. For cab class, again, the x-axis is each model, 4 different models. Green line is the TCAV score for image concept. Blue line is the test accuracy. So you want to look at some blue line being close to the green line, or at least the pattern is similar. For cab class, interestingly, it always looked at the image. It never looked at the caption. We have some hypotheses why we did that, but even if I gave 100% correct caption, it always looked at the image. So you can see the TCAV image, green line is similar to blue line. That's cool. In cucumber case, slightly different. When we give perfect caption, it actually looked at the caption. So the test accuracy was low, which is again reflected, followed closely by TCAV image score pretty low. So what this tells us is, yeah, if you have a ground truth, then we can show that the TCAV follows that ground truth. You might ask, though, well, the saliency map that you talked about before, does that work too? Well, let's have a look. Here is an image with a caption for each of those 4 models. And remember, the ground truth was that cab always looked at the images. Here are 4 different saliency map methods, each column. Some saliency map doesn't highlight the caption, but some saliency maps do highlight captions. And as a human looking at it, I don't know which one was more important. And you might say, well, Bean, but like maybe this is cherry-picked example. Maybe. So we're going to run Turk experiment. So we selected cab and zebra and cucumber. We asked 50 Turkers to judge which one was more important. Was it the image or was it the caption? We also asked, how confident are you in your answers? And the result is interesting. So here is one of the saliency map results for one of the classes. Smooth grad is for yes.
Sorry to interrupt.
Yes.
But isn't the question more along the lines of what you are visualizing is essentially the support space rather than the relative weights that are associated with those pixels or with those activations?
So think about this way. So say the saliency map return support, not the evidence for prediction. What would be useful as an explanation for neural network is something that you use to make prediction, right? And this is in fact the story that these methods tell in their. In fact, I have one of the saliency methods of my own work where we believe, well, yeah, these are highlighting pixels that are important for prediction because it is high score on the when I take the derivative. So that's the story. So imagine, in other words, I have a cancer cell, and I'm looking at this cancer cell as a doctor, and I want to know why this was predicted as Gleason 3. Then I want to know which parts are not just parts that were looked at and decide to disregard. I want to look at the parts that were actually used, right? And I think it might be the fact we have some other work that comes out that tells us it might be that it's the support or edges or other just important structure in the image that saliency maps are looking at. But that's more TBD. So here's the results for Turker experiment. The first graph shows cab for this particular saliency map method. 2 models are shown. For this model, Turker, well, let's look at this model first. for this model, Turkers were split in half. Half of Turkers said it's an image. Half of Turkers said it's a caption. And they couldn't agree. For this model, Turkers did agree. They agreed that, yeah, captions are important. But remember, cap class always looked at the image. So this is actually a wrong thing to agree on. And I'm showing the TCAV results in contrast, where it closely follows the ground truth. More, yes? No, it was wrong based on ground truth, because we can test the accuracy of these models using an image without the caption. Right? If it does well, then it uses the image. If it doesn't do well, it didn't do well because I didn't give you the caption. So it's a ground truth. Good question. More alarming thing to me was that humans are really confident when they answered these questions. These are the ratio people who marked, I am the most confident, as confident as I can be, when they're correct and when they're not correct. See, that's really alarming, and it might be, for someone with HCI background or visualization background, might find this like, yeah, of course. There's a confirmation bias. When human looks at an explanation, they pick out the information that they want, they like, only the things that they agree on. So yeah, this is showing that. This is not to say the saliency map methods are incorrect and not valuable. It is just to say that we need to use this method with caution, especially for high-stake decisions. All right, yes? I asked, we gave them some practice questions, and we gave these four pictures along with the saliency maps, and asked, these are the captions and these are the images. Which one do you think the model used to make a prediction? So in other words, if I see image with like highlighted caption like this one, then Turkers might say, oh yeah, the caption was important for the network given the saliency map. If I don't have highlighted in captions, then it means that, oh, saliency map thought network didn't care about the captions. Does that make sense? Yes?
I'm just wondering how does this concept activation method generalize for different categories? In one sense, do you always see that each category has a particular unique concept activation vector, or in the sense, for example, the concept of the vector which is representing a zebra could also represent a chessboard?
Oh yeah, so you're asking, was there a correlation? Can this vector mean multiple things?
So if they are shared vectors across different contexts, how does that affect the interpretability?
Yeah, it's a good question. So the statistical testing, if there's a superset of concepts, let's say animal, and here's my zebra vector, and you're asking whether, well, zebra vector ought to have animal vector too, because it's a superset. Not necessarily. So the statistical testing is going to tell us that whether the animal vector can be linearly separated from zebra. So if the vector also contained what it means to be animal, it wouldn't pass the statistical testing, because to the network, these are the random images that you're sampling from. Does that make sense? So yeah, but it doesn't guarantee that it will not have, if you have a vector, a concept, that always occur together, like always, all the time, then yeah, you will probably have correlation. Okay, I love good questions. All right, so after the sanity check experiment,
yes. I have a question, ask it now before you move on, which is that the whole the idea of using this concept vector with a directional derivative is sort of seems to be predicated on this notion that whatever concept you're looking at is somehow a graded concept, that there can be more of it or less of it, and it's the direction that matters, as opposed to a location, meaning all the stripes are clustered here in this m-dimensional space, whatever the dimension of that layer is, and everything that's not stripes is somewhere else. Mm-hmm. Like, I'm thinking in particular of binary concepts. Concepts are not graded. So I'm wondering why the choice of this directional derivative with respect to a plane as opposed to, for example, distance from a location or the derivative in the direction of a location. You could have computed the centroids of all your, the center of all the stripe projections and then maybe seeing where the non-stripes live. And if they indeed live on one side most of the time, then maybe a plane makes sense. But if they're scattered all around, then perhaps location. In other words, I'm wondering whether you did some further analysis of your concept, how this concept is represented in your intermediate layer.
So how is
what kind of derivative makes sense?
So I think there are multiple questions in your comment. So let me try to disentangle. So one question was that it might be I have three concepts. Let's say stripedness, zigzag, and dotted, and they're just in different locations in the activation space. Now, why am I just stripe and non-striping? And why do I do just binary as opposed to like 3-layer consider thing?
Think of it like that. That's even in the case of just stripes. That why is it reasonable to think that stripes will be somewhere on one side of the plane as opposed to in one corner of the space? And if it's in one corner of the space, then the plane is arbitrary. I want a sphere that encircles.
Got it. I see.
Stripe.
I see.
Projection.
So if it's rotating across the space and it's a plane or it's a line and your VCL basically points in all sorts of directions.
So let's say that all my stripes were in some part of the space and this will be hyperplane that separates it from the non-stripes. And now I'm looking at the image which is way out there on the other end of the line. Then the directional derivative perpendicular to that separating hyperplane is less meaningful than the derivative in the direction of where the stripes projections actually live. You see what I'm saying?
Yeah, I think we need like a whiteboard to describe this because a lot of intuitions that we have about the high dimensional space, I learned to not trust my intuition that these things don't hold. So I'm not sure how. Yeah, let's follow offline. I'm not sure how that will practically make difference in this case. Like, does the direction matter versus learning hyperplane? I'm not sure. Which one is more robust? Can we learn more sophisticated CAV? Yeah, I'm not sure.
Or just look at where the things line up and ask what is the right separating surface.
So if you have a surface of a plane instead of line.
No, what I'm thinking is that, for example, if you decided to find the best linear separating hyperplane, right? What if you had tried to enclose the projections of the stripes in a sphere?
I see. I see. Okay, so that question is a lot more streamlined. Yeah. So can we learn? Your question is instead of linear, can we learn more sophisticated, like a sphere?
How is this concept represented in your concept space?
Yeah. So this one is the simplest way to learn your concept vector. If you want the sphere and therefore have some point-dependent CAV, depending on where you are, you can totally do that. That will probably give you a better estimate. Yeah. So it's the simplest method.
I have no intuition for it. That's why. And in fact, quite the opposite. I have no intuition of what things look like.
Yeah, same here. I think we're just humans, being a human. Yeah, so sophisticated CAV, you can totally learn it. I haven't done it. Probably would need a lot more work. But good questions. All right. All right, so after the synthetic experiment, we went wild. We were really excited. And we ran these set of examples for Googlenet and Inception V3. And for those who are not familiar with the Inception V3 and Googlenet, these are one of the highly performing image classification networks that is now publicly available, used everywhere as a backbone for a lot of other analysis. So we are interested in what sort of biases and importance of concepts these networks have. First one, we tested the color. So this is to answer your question. We tested color concept by generating pictures of R's, red, green, and blue. And we show that fire engine, red is important in fire engine, green is important in fire engine because a lot of fire engines are sitting on the grassy field. This makes sense if, anybody from Australia? No Australia. Okay. Unless you're from Australia, in which case apparently in some Brisbane or some part of Australia, fire engines are yellow because some visual context, apparently that's a better contrast for humans. So maybe it's encoding geographical bias. Some other experiment we did is rugby ball is being particular race is important in classifying rugby ball. And that makes sense because I'm from Asia and we don't play rugby. And in fact, this is not new. This is qualitative finding from this previous work where they passed a white person's face and it thinks, oh, it's a rugby ball. Here's another network, Inception V3. Again, similar finding, confirming previous literature. Ping pong ball, Asian, because I'm from Korea and we were pretty good at playing table tennis. We've won a lot of gold medals. So yeah, the training set reflects that fact. Oh, not just Koreans, I guess. No. And one of my favorite thing is dumbbell. If you remember the very first deep stream blog post, they found this neuron when they passed dumbbell. They found this neuron that highly activated on muscular arms, and they made a conjecture that maybe arms matter in predicting dumbbell. And now we have a quantitative confirmation. Yeah, the arms did matter. And for this one, I didn't have arms classes pre-collected, so I went to Google image search, collected 33 arms pictures, and plugged it in. It is still able to confirm and pass the statistical testing. So now finally, we were yes. Sorry? This is a TCAV score. Good question. So it's between 0 and 1. Higher it is, more important. Oh, I see. No, I only tested like race, gender, and like texture, things that I had. That's correct. Yeah. That's totally correct, and it's a valid point. In my interest, part of my interest was the fairness experiment, where I have some idea of what protected group should be, my minority, race, or gender, or other types. So in that case, it fits well. But you're totally right. The selection of the concept would reflect some of my bias. Yes.
Just write all of the concepts, or
yeah, we could.
Possible space of concepts.
Oh yeah, so my dream is it would be really awesome if I have a dictionary of concepts, which we can build, right? The data sets or ImageNet are built. You can use just the ImageNet, what is it, like 100,000 classes as a basis of the examples, and just you can do the whole thing. I just didn't do it. And you had 2 questions. Oh, lots of questions. Let's go from you. You have a nice question. Oh yes, thanks for pointing that out. It's a layer. It's the names of layers in Inception V3. So I actually point out interesting thing actually, maybe this one. So, oh, maybe not. Okay, so in this case, the color, this green was lower layer than this red one. And what that means is that other layers, well actually I'm not showing all the layers here. So I discovered that the texture or lower level features had passed the statistical testing in the lower layer, and the high abstract features like race and gender passed it later in the layer. So yeah, it just differs where you're looking at. Yes, there were lots.
So the way that you've described TCAV, it's always positive, but I wonder about negative concepts, like arms are a good indicator of dumbbell. Is legs a negative indicator of dumbbell, which means you would flip the classifier and use the CAV for non-legs instead?
Yes, you can do that. But I think I haven't tested it. It in theory should work, but I don't know. And there's a question.
I mean, you already answered my
Right.
in the sense I was going to ask that we have the intuition that lower level concepts are learned in the earlier layers and higher level concepts in the later layers. Have you tested that, or can you set up a hierarchical set of concepts? I think in the second page you had a better study of, you can put arms and legs and stuff in one, and then you can put people in the next layer or level, and then study whether the layer at which these concepts are disentangled is in order.
Yeah, totally. We can totally do. Actually, I'll show you. I'll show you in the last slide, like the accuracy. We plotted the accuracy of these classifiers that return VCLs, and you can see this trend that lower level layer, lower features are high accuracy already in the first layer. And it's not really answering your question, but just saying that, yeah, it's a fun thing. All right, yes.
I'm curious, what is this curious TCAV? Really take a class that shouldn't have anything to do with the dumbbell. Do you still see anything non-zero in terms of TCAV?
Oh, will I see a concept that is non-zero?
Yeah. So if
Yeah.
I take one of the 1,000
Yeah.
classifiers, or one of those is going to be fine.
No, it's not because a lot. So high dimensional space. This kind of goes well with my intuition that a lot of things, because your number of classes, 1,000 classes, right, in this Inception V3 is such a small number compared to all the possible directions you can go. In higher dimensional, if you the 2 to the n dimensional, it's so bigger than the 1,000. There are directions that doesn't do anything. So in other words, it's the opposite of finding adversarial examples. Adversarial examples, you're guaranteed to find this direction that will flip the label. It's also possible to find a direction that you can go as long as you want, but nothing happens. So yeah.
So does that actually show on these drawings really the way they come?
I haven't done the experiment. It would be a fun experiment to do, yeah. But I know that such direction exists because of some of my other experiments. It's a weird thing, neural network. All right. So now we're gonna visit some real world application. Diabetic retinopathy is a symptom or what do you call it? It's not a disease. It's a thing that if you find it early, then it's treatable. If you left alone untreated, then you might go blind. It's important. And so people had worked on building a model. Given this retina image, how accurately can we predict level of DR? So 1 from mild level of DR to 4, which is most severe level of DR. So my question is, well, this machine learning model seems great, but can we ask the model whether the concepts it's using is consistent or inconsistent with diagnostic concepts that doctors would have used? So first, we went to a doctor and asked them, what are the concepts that you use? And she said, well, for DR level 4, which is a higher level of DR, we use these concepts abbreviated because I wouldn't be able to read all the words. That we look for these concepts. If these concepts exist, it's DR4. But I also look for what does not exist, like this one. And in different level, I look for different things. So then we ran TCAV on these concepts. We had images that are tagged with these concepts, which is part of so we were able to provide the example for these to learn the concept vector. For this class where model's accuracy was really high, we showed that, yeah, the model is using the diagnostic concept that doctors are also using. So the concept VB is low, the other concepts, green concepts that should exist in this class are high. It's good. But for a class where accuracy was medium, slightly different story. We learned that this type of concept, which is type of hemorrhage, it's like when you look at the retina images, it's like a blood vessel that's kind of blown up. It showed that, well, to predict level 1, it was using the concept it shouldn't be using. And we were like, oh, why is that? Well, because the DR level 1, which is a class, that it is often confused with DR level 2, which is the next severe level of DR. And in DR level 2, HMA is one of the most prevalent feature. So the TCAV is correctly pointing that, yeah, model is using this feature that is important for other level, not my level. So that was fun. All right, to recap, we talked about this method called TCAV, quantitative global explanation of using high-level concepts of your choice, given examples of the concepts, positive and negative examples of your concepts. And this is circling back to my first research agenda, to really assure that the model that you're using out in the wild, making important decisions, reflect our values, such as fairness. And also, we can ensure that domain expert knowledge, like doctor's knowledge that we care about, the data or machine learning models may not have, are appropriately reflected. So with that, more questions. Thanks.
So what if they're not? So what do you do
Oh, yeah.
with the model?
Good question. I'm working on it. There's been a lot of good work on debiasing embeddings and neural network models, and they work to some extent. I think, again, being in a high dimensional and not really understanding in depth what's going on, I think we should be very careful about how we're warping that space. And simple unbiasing techniques might work, but we don't know the unknown unknowns. We don't know what we're losing, who else is compromised. So to answer your question, I don't know, but it's a highly active topic. Yes? Oh. How do you suggest testing that? Like taking the derivative of... Oh, I can like collect all the red pictures and test the red color concept. Ah, I see, got it. Yes, we can do that. I need pictures of red things. I guess I don't have it. I thought one thing that I did try to do was cucumber. I thought, of course, cucumbers are green. I haven't never seen non-green cucumbers, so I collected all of them and I tested the color concept, and red comes high, and I was like, that's weird. And I looked at all the cucumber pictures, and guess what was next to cucumber all the time? Yes. How did you know? I didn't know. And I was like, oh, okay. So I couldn't even do that in that manual sense. Maybe I can do like average value of the person. I don't know. We need an ad hoc to collect those pictures. Yeah.
So I'm a little bit concerned about using examples for a concept. So you mentioned like how much does female matter for the doctor.
Mm-hmm.
But if I understand correctly, you're comparing like, so you come up with a bunch of examples of females, and then you compare them to totally random images. I mean, the system is seeing, oh, here's nose with certain distributions, here's eyes with distributions, right? And if you go test it on a doctor, I would expect that you'd see a fairly high score. Like how much does being female correspond to being a doctor, and how much does being a table correspond to being a doctor? Right? Like, am I
I don't know if I understand your question. So is there like a subset of a doctor, female
so
images?
Like you would want to compare for gender, an example.
Yeah.
As an example, you'd want to like build a hyperparameter like between male, female, non-male, and random, or female and random.
Oh, I see. If you know the class is binary, why don't I just go do male versus female and not male? So there's a history reason for why. So we first tried that pairwise CAV. So instead of picking at random, we tested on dotted, zebra, and the texture example we did dotted versus zebra, dotted versus zigzag, and striped. And we learned relative CAVs and tested on that. But we decided that would encode our bias way too much. And it's unclear if we do that, how to do the statistical testing. So I'm comparing these three things and three things only, right? So whatever that is correlated with more with stripes, but less with the zigzag, will become part of this vector. I just don't have any other choices, right? Because it's not random.
But it feels like you're doing that now, because if you give it a bunch of examples, you're also giving it a bunch of examples of human.
Right, but random vector testing filters that out, right? Because if my human vector, there's a human images here, and there is my woman image here. If I do the random testing, it's gonna chop out the human part. And if my example fully represents the human, then it will not pass the test.
So you're relying on not male examples showing in random cases that it's significant.
I guess maybe better put it this way. I'm trying to learn a classifier that is more tighter on classifying women versus others. Because if I just do woman versus man, and they're far away from each other in the activation space, I can put classifier anywhere, right? Whereas if I do woman versus everything else, then I have to put classify right here. Right.
My question is about where the labels come from. Are they coming from captions? And I'm curious just because of the issue of reporting bias. And so, for example, the relevant concept of red or fire truck. I assume if like humans were writing captions,
Right.
they would say red fire truck, they would say fire truck, and how that.
Yeah. Yeah, it's a good point. So the examples, it's a garbage in, garbage out, as goes some other things. If your data set that you give me as a concept is biased, then there is very little we can do. So if it's biased, maybe you can check. Yeah, if we have that dictionary of concept that we talked about, maybe you can check for biases in your concept as a start, but we haven't done that. Yeah. Okay.
So this thing, the speaker.
Thanks.